I'm Joe. We're going to talk about Kubernetes, possibly the best thing in all of mankind. Oh, it's so good. You're not even ready for it. Yeah, that's me. It's my final year in the cybersecurity program. If I did my math right, that means it's my final RITSEC presentation while an RIT student. Big sad. From the great place of Long Island. I do pep band, keyboard, sys for CSH, ham radio, fun person. Now it's getting warm. You can catch me on the Greek lawn with a big wire, trying to talk to Italy. Feel free to talk to me about Rust, past co-ops. I worked at MITRE last summer, and this summer I'm going to Citadel in Manhattan. So what is this magical Kubernetes? What is Kubernetes? What does it mean? Why does every interviewer think they need to ask you about Kubernetes? Kubernetes, in the official documentation, is an open source system for automating deployment, scaling, and management of containerized applications. Now, what does that mean? That means that you are orchestrating containers at scale to deploy your applications. So whenever you have an application that you're trying to run in a container, Kubernetes is there to help you keep it up at a good level and actively scale it as needed, as you have usage on your website or application. It was developed by Google in 2014 and has since kind of won the orchestration battle. So when people realized that containers were going to be like the way to go, a couple companies were fighting to see who could make the best container orchestration system. The two main ones were Kubernetes and Docker Swarm. You can still probably run Docker Swarm. You shouldn't. Kubernetes kind of won outright, which is why it's all you hear about nowadays. So backtracking, what's a container? What is it actually orchestrating? For more details on this, I would check Scalz's presentation on containers and Docker from last semester. But a little rundown, it's a collection of files that your kernel and file system are sharing that are more efficient to use than a virtual machine. So as you can see here, instead of with a virtual machine where you have to spin up a hypervisor and an entire guest operating system with its own file system, its own kernel, you're just sharing it with the host OS through the container engine. This saves you storage, it saves you resources, and it saves you time. It's native for Linux. Windows is working on like Windows container images, or specifically on Windows machines. And whenever you run Docker or another container in a non-Linux environment, Docker or your container engine is actually spinning up a virtual machine to run all of the containers for you. So now we know a container. What is container orchestration? So let's picture this. You got the RITSEC website. You got to make one container for the RITSEC website. Now let's say it starts getting famous. Let's say, it's ISTS or, I don't know, something happens and everyone wants to go on the RITSEC website. How do you handle the increased load to the website? You could make more containers and then put a load balancer in front of it against Nginx. But, what if you start, even with all these containers, maxing out the system you're using it on? Do you just keep adding more CPU? Do you download more RAM? Eventually, you're going to hit physical limit. So what Kubernetes tries to solve is that issue, that instead of vertically expanding your system, you can horizontally expand. So what that means is instead of adding more resources to one machine, we're just going to add more machines. So what are Kubernetes nodes? Nodes are the physical machines that make up a cluster. Kubernetes, 99% of the time, is designed to work in a cluster system. There are many environments that will let you do it with one node, either for low-scale applications, for learning how to use it. But 9 times out of 10 in production, you're going to see a cluster such as this. So the two main terms you're going to see are master node and worker node. The master node are typically kept in odd amounts. So you'll see 1, 3, 5, 7, 9. And these are to handle all core applications of Kubernetes. So that's the API that you interact with to make things change. That's scheduling your pods. So whenever you ask Kubernetes, hey, can you spin this up for me? It's going to look at the master node, say, figure out how to make this happen. and it's going to find which worker node is actually going to run your application. Another cool thing that it runs is called etcd. etcd is a distributed key value system, which is used by Kubernetes to maintain state. So everything that happens in Kubernetes is kept track in etcd. That's how it ensures that you are maintaining the state that it wants you to have. Worker nodes, this is where all the fun happens. This is where you actually run your application. So all worker nodes will run what's called the kubelet. The kubelet is what the master node will communicate to, saying, make this many containers of this image with these volumes and make it now. It'll also do things like network proxying, so all workers will be able to communicate with each other, and all pods across workers will talk to each other. And other cool things such as DNS, the UI, if you have a UI for your cluster, and all that good jazz. So at the end of the day, the developer will only care about the master node, because that's what it's using to make changes and make sure that the application's up. The user only cares about the worker node, because that's where the application that they want to access is actually living on. When you're running this at scale, there's many ways that you could handle getting the user to the worker node, because you don't want them to go to one node that's not running the application at the time and then have them fail. So some of the ways I've seen have been HA proxy, which is a layer 4 TCP proxy, or doing DNS round robin. So you simply set your domain to every worker node, and then it'll get to one of them that has the system running. So that cool Kube API, you wanna use your Kubernetes. You wanna talk to it. You wanna make some pods. You wanna make some deployments. You wanna see why your stuff isn't running. You're gonna love this. Everything in Kubernetes is done through the command line. There are UIs. There is a HTTP API, but 9 times out of 10, it's easier to just use the command line called kubectl. Kubectl follows a very verb noun system. So a lot of it is kubectl, get, describe, create, edit, and then the resource type, otherwise known as the kind. We'll get to that in a minute. So the main ones you're going to be using, kubectl get will kind of just show in a high level what's running in your given scope. So if you say kubectl get pods, it'll show all the pods. It'll show like the name, how long it's been running, if it's alive. Describe will show it in a lot more detail. So you'll be seeing the logs, you'll be seeing more exact YAML, you may be seeing some errors in longer syntax, you'll see the image it's running. Create, self-explanatory, it will make something new. You often got to provide a bit more fields, just to kind of specify what you're trying to make. And edit, that one, it'll open your default editor and allow you to edit the manifest that is allowing this object to be made. The default, I believe, is Vim for kubectl. At the end of the day, it's YAML, so you'll be able to edit it as you need. Another important one that I forgot to mention here is apply. So if you do kubectl apply, provide it with a YAML file, it will try and apply whatever's in that YAML file, whatever resources are needed to your cluster. This is very cool because also kubectl is idempotent. Similar to Ansible, if it sees something doesn't need to be changed, it will not change it. So if you just want to make sure your system's in a current state, you can run kubectl apply. And if it needs to change something, it will. If not, it will say, you're good to go. So I keep talking about resources. What is a resource? Everything in Kubernetes is a resource. Your pods are a resource. Your config maps are a resource. And every resource has a kind. Kind, you can just think of it as a type. So the kind is what exactly you're talking about. What is this object? What is this resource representing? The kind is what will determine what fields you need in the rest of your YAML file. The most common fields you'll see at a high level are the spec or specification and the metadata. So spec will have stuff like, for a pod, what image is it running? What volumes is it mounting? And metadata will have its name, its creation time, its UUID, all that stuff that it's cool to have but isn't needed for running the container. Pods. We're not going to talk about pods of whales. That's actually where the name came from. Because think about it, Docker, whale, multiple containers, multiple whales. pod of whales. Think about it. This is the most basic compute structure that you'll see in Kubernetes. Everything ran is in a pod at some point, but a pod can have multiple containers. So you will not individually deploy containers in Kubernetes. You will deploy a pod that may just have one container. Instances where you'll have multiple containers in a pod, you'll see a lot in like the Kube API, that each pod will have its individual health check, and that health check will be checking its individual instance of the API to make sure it's running correctly. So the pod, it will define what image it's running, what volume amounts it has, and what environment variables need to be running. It's very similar to what you might see in a Docker Compose file, where you're defining, hey, I need this image with these volume amounts and these environment variables. Very rarely you'll see just a pod being deployed, because the pod itself will not replicate. So what that means is once the pod dies, if it has nothing behind it that's helping it, it'll just die once it's over, and you won't be able to get it back. Here's a bit of YAML on kind of what you'll see if you look at a pod. So I just kind of grabbed from a test RITSEC CTF deploy, which y'all should check out. So one of the things you'll see here, this is for the MariaDB. So it's running. So you can see in the metadata section up top, the name of it. It gets a random name through a deployment, which we'll get to later. And a namespace. Namespaces are kind of like projects that you get to define. So you can have users that just have access to the one namespace instead of all pods within your cluster. So in specification, we're going to define a container, and we're defining some environment variables from other resources, which we'll get to in a minute. The image, we're using MariaDB latest, the name of the container, and then some volume mounts. Right here you can see we're mounting Vault, MySQL to something called CTFD MariaDB data, which again I'll show once we get to the persistent volume. Also below, I'm just going to mention this now because I cut it off for the rest of the presentation because it gets too big, is the YAML will automatically be updated with the status of the application or the resource. So here you can see the container ID. Kubernetes by default often will use Cryo instead of Docker, or you'll see some using Podman. You can see the image that it's using, the image ID, and other information such as its host ID and host IP. Kubernetes is very good at creating internal IP ranges for different systems. We'll get to that when we get to networking. But at a high level, all the pods will have their own individual IP. Pod debugging. Yeah, sometimes pods don't go the way you expect. You'll see a lot of cool errors pop up when Kubernetes is upset at you. Some of the ones you'll see are called crash group backup. Kubernetes doesn't want you to constantly be creating containers, having them crash, making a new container, having it crash, because that's not good resource usage. It's not fun. So crash group backup means it's going to, as it keeps crashing, it'll take longer and longer to make the new container. So it's giving you time to check out the logs before it deletes the container and makes a new one. Another one you'll see, which is a bit more self-explanatory and easy to fix, is the image pullback off. That just means it's failing to pull the image. Check your Docker IO. You may be having an issue or the image does not exist. There's also cool things in kubectl. You can do kubectl exec, just like you Docker exec, to enter the container. See, hey, why are you crashing? Are the files okay? Is something going wrong inside? And you can also do kubectl logs to look at the logs of the container and see, oh, is like the API not talking to itself, or are we having troubles with the database? That's all cool stuff to help debug. At the end of the day, it's very similar to Docker at this point, where you're just trying to see why your application isn't working. Deployments. So we made pods. How do we make sure those pods are running at all times? How do we make sure that the pods are being scaled whenever we need more, when load gets high, whenever the RITSEC website goes famous? So what you gotta do is you gotta make a deployment. A deployment defines a collection of pods and their needed components. 9 times out of 10, you'll be deploying deployments. It'll handle everything for you, including pod count. So as you can see, when you make a deployment, it creates these things called replica sets. We don't gotta touch those; those are annoying. And the replica set is what ensures that the amount of pods you want for each type of pod will be created. And then the pods, which node they're assigned to, is done by the Kube API scheduler, which is on the master. It all comes back. Here's some deployment definitions for how to handle deployments. As you can see, inside the template section down here, it's very similar to the pod that we saw before. Up top, we just have stuff such as the replicas, which is how many of this resource do we want at one time. Stuff strategy. So there's different ways that if the pod needs to be recreated, such as the image is updated, you change the environment variable, and needs to redeploy. Rolling update means that it will keep the old version running, skip, bring up the new one, make sure the new one is okay, and then take down the old one. The other main one is recreate, where it will just turn off the old one, or you have downtime for a little bit, and it'll bring up the new one. You'll see that often if you just don't want to have two things running at once. It's a bit more scary because you may end up with nothing running, but sometimes it's needed. Networking. I said we're going to talk about networking. It's going to be fun. So there's 2 internal IP ranges, sometimes more, in Kubernetes. You have podnet, which is where all of the pods are living. So each pod gets its own IP. The containers themselves do not have their own IPs. They share an IP. So localhost on one container can represent itself or the other container in the pod. And then you have service net. Services are the way that you expose a pod to other pods in the cluster or to the internet. So by default, Kubernetes will not allow a pod to talk to other pods. The internet cannot talk to a pod unless you explicitly tell it to. To do all of this, we need these cool things called services. A service, as I said, it exposes a pod to the internet. There's multiple ways that you can do it. Cluster IP, this will give a new IP to a service, usually in ServiceNet. So if you have a MariaDB that needs to talk to your application, you would give the database a cluster IP, and then you would tell the application, hey, you need to talk to this internal IP to get your database. Load balancer, this, as it sounds, will balance the request to the application across multiple pods. There are multiple implications of this depending on which type of Kubernetes you're using. Some will use Nginx, some will use other load balancers, similar to Ingress, which we'll get to. Node port, you'll see this a lot with TCP applications, not typically HTTP because that has Ingress. So Kubernetes will, I believe it's 30,000 to like 33,000 TCP ports, like the range. That will be used for node port. So if you specify node port, you specify the internal port on the pod that you want to expose to the internet, and Kubernetes will give you a random TCP port that you can use to access the application. Finally, Ingress. This is a cool one. You'll see this a lot with people who are making web applications. You are able to specify domains, paths, whatever you can do with HTTP to proxy incoming requests on 80 and 443 to all of your applications. So in this example, if you have foo.mydomain.com, that would go to maybe one service with one set of pods. mydomain.com/bar would go to this group, and everything else would go to this group. So this is cool if you have, let's say, one set of pods for your API and one set for your front end, or just if you're running so many different websites, you need different domains. Ingresses, again, very much depend on how you implement them. The main one I've seen is Nginx. Nginx have really taken over as a very good, easy to set up ingress. I've also had HA proxy working very well, but I didn't have that much experience with it. Often you can see also what's called a cluster operator for these, where they will handle HTTPS certificates for you. So there's one called the Acme operator, which will use Let's Encrypt to give you fresh certificates for any time a new service is made for the ingress. Service definition. So we can see here, again for the MariaDB, it's given a 172 address, which if you remember from the pod definition, which was on a 10 dot. So again, different IP ranges. And then you can see we're talking about port 3306, the MariaDB port, and it's exposing on the service again as 3306. You can change that as needed. They don't have to be the same, just as for this example. And I'll type, it's being blocked by captioning, but down there it says cluster IP. Ingress, 1 second, is my charger over here? I thought I was dying, dude.
What port surge do you need?
See? I got it. Technical difficulties. I did that before. It's okay. It don't matter. Ingress is, as I was saying, very good for HTTP, HTTPS traffic. You use them to define domains and paths to specify which services to talk to. And again, Nginx HA proxy. I kind of rambled on this in the last slide. So now we're going to talk about persistent data. Often when using Docker Compose, you'll run into, oh, I don't want my database to reset every time I tear it down and spin it back up. I want to hold that data throughout different containers, throughout different pods. So now we have persistent volume. Persistent volume and persistent volume claim are a bit of a weird concept when you get into them. So persistent volume specifically means this part of data is available to use. It's not assigning it, it's not usable by a pod. Just saying this 15 gigabytes is available through this provider. Those providers, that can be your S3, that can be your Ceph, that can be a local volume on one of the nodes. There's a ton of different available options through the Kubernetes API. It's very much usable to whatever environment you're having to use. Once you have a persistent volume, you can create a persistent volume claim. The claim will specify how much storage it needs for its application, if it needs a specific node, if it needs a specific file system. And when that happens, the Kube API will look and say, do I have any persistent volumes that match these requests? If it does, it'll bind the PV to the PVC. And at that point, they are bound. The PV cannot be used by any other application, any other PVC. Once the PVC is made, now you can use that in a pod and mount it to a volume. So here we just have more YAML, more definitions. So here we're going to go into some more cool things that you have to do. You can see, mouse work on here? It does. Access modes. So depending on which provider you're using, some access modes are restricted. So read write many means that multiple pods can be reading and writing to the data at the same exact time. Some, just due to the way they're designed, can only be read write once, maybe read write to one pod and then read only to other pods. So defining what your available access modes are is important because those must match between persistent volume and persistent volume claim. Here we're defining a 25 gigabyte persistent volume, and this is using NFS, another cool option you can use. So if you have one server that has your NFS data that you want to bring into a container, you can specify the path to NFS in the server, and it will allow you to communicate over NFS to get all the data to your pod. In this claim, you can see the access modes are matching, the storage is matching, they both have a volume of the file system, and you can even do here where you specify exactly what persistent volume you want it to use instead of having the Kube API try and think for itself. And you can see at the bottom, these are both bound. So they found each other, they're binded, they're happy, and now they can start working. Another form of persistent data is config map and secret. These are ways that are commonly used to either store file data, individual files, or handle environment variables. So a secret is, as it sounds, a config map, is a key value pair that's stored in plain text. So this way you can keep stuff such as your MongoDB values. And then in the container, in the pod, in the deployment, you could say reference this config map for your environment variables. So here you can say, so when the pod's created, look at the config map, and it'll take all the keys, make that the key of the environment variable, and assign it to the respective values of the config map. Secrets are very similar. You typically only use them for passwords. But an important thing to note is that secrets in Kubernetes are not encrypted. They are base 64 encoded. The main reason of why they're separated is for role-based access control, which we're going to get to later. Because at the end of the day, you need to access the data, so there's not very much ways that you can encrypt it without making it unusable. That's something that people will often get confused when they first look at a secret. Another cool way that you can use config maps is for static files. So if let's say you have an nginx container and you know you have a static nginx.conf, you can, as you see here, you can just define a file name and the data. Then in your volume for your deployment, you can say this volume is actually just a config map, which is very cool, especially when you have very static applications that don't need to write to the file. They're just read from the file, you can use the config map. Again, we got some cool examples here. So you can see for MariaDB, that's a database. You got random loop password set to true. You got CTFD. And for the secret, I removed it. You're not getting my MariaDB password. You could try. But just imagine here, it's base 64 encoded. So now you learned all this stuff about Kubernetes. You are dying to use Kubernetes right now. How do you actually use it? You can deploy straight up Kubernetes. That works. Some other cool examples I want to highlight. Micro K8s. It's a canonical thing. I believe it's through Snap. It's a one node Ubuntu instance. You can install Micro K8s, and now you have Kubernetes on one machine. It's very simple, very fast, very efficient for just learning and getting used to it. Minikube is cross-platform, very similar to Micro K8s. Very easy to deploy. I believe they also support Windows and Mac if you want to test it out on your non-Linux machines. You got K3s. I think I never mentioned it. Abbreviation of Kubernetes is K8s. So K3s is a subvariant of Kubernetes, mostly designed to deploy into IoT and edge devices. And the two that are kind of more like enterprise level are Vanture and OpenShift OKD. So Vanture is built by SUSE, and OpenShift is built by Red Hat. And OpenShift also has an open source variant called OKD. RITSEC actually runs an OKD cluster. So if you want to check that out, hit me up. I'll teach you how to use it. All right, so you made a cluster. And, we talk a lot about YAML. YAML's annoying to write. You don't want to mess it up. It's pain. You got Helm charts. Imagine a package manager or your Kubernetes. That's what Helm is for you. So here you're able to add repositories, and you can simply, if someone already made a Helm chart for the application you want, you can have it install into your given namespace, and now you have it all deployed without having to think about it, without having to do every single YAML file by hand. So now at the fun part. We have for security. How do you protect your kube? One important thing is the anonymous user. Some kube clusters will have anonymous users on by default. You want to turn that off. Just not good. Another important thing, some will use by default, but you can enable Kubernetes to run all containers rootless. So if you ever use Docker, you know when you exec into a container, it's running as root. That's helpful when you just want to get stuff done, but it's also helpful when an attacker gets into your pod and now they're root in a pod. So you can assign Kubernetes that for every container, you want to assign a random UID, so that way it's unprivileged and you don't have to worry about it. Also, with logging and auditing, the Kube API can log so many different kinds of events. If you create what's called an audit policy resource, you can define exactly which events you want it to log. Then you can have it log the files, you can have it push to webhooks at given periods. There are a bunch of other custom third-party applications that are able to monitor your kube cluster for you. Now I talked about Abbate. I want to talk about secrets. This is one of probably my favorite features about Kubernetes. The role-based access control in Kubernetes is very easy to follow, and it's very, very powerful. So the way that, if you ever use role-based access control, the way that it works is that you assign all of your privileges to a given role, and then that role is binded to either a user, a group, or a service account. And all of the different privileges that you can give follow very similar to how the Kube API works when you're looking at it in the command line. So you're able to tell it the role only allow certain operations with certain different types of resources. So let's say you have a developer that shouldn't have the secret or the database password, but they should be able to look at the logs of their application. You can say that it's able to look at and manage the pods and the deployments, but they can't manage the secrets. That's one of the big ways they can really tighten down on who has access to what in your kube cluster. Very helpful for when you have a large enterprise and need to handle different people with different privileges. So attacking. You want to use this defensively. The API and etcd is the main key value store. Both of those have the potential for anonymous access. If you have anonymous access, you can really get a lot of data. You can try and find some open secrets. You can try and find some places that you can create pods. It's very fun. There's also sometimes what's called the Kubernetes read-only port. That it won't let you write to anything, but sometimes if it's exposed, you could get a lot of data. Really try and find as much as you can. Potentially, again, find some secrets that are exposed somewhere. For node ports, you can try and poke at any of them, see if there's any applications that you know of, and that may be vulnerable. And again, once you're in a pod, it's just like a Docker container. If you can find a Docker escape somehow, you can try it, and now you'll be in a worker node. If you manage to get API access, I was actually introduced to this during ISTS. There's a repository called Bad Pods. Bad Pods is a collection of Kubernetes manifests designed to help you break out and get into the actual physical systems. It's very cool. I highly recommend checking it out. And here we just have a bunch of resources that I found while getting research for the presentation. Some on just general Kubernetes, attacking, bad pods. Google Cloud is also very cool. Since Google made Kubernetes, GCP is very good at cloud Kubernetes platforms. They can get $300 of free compute because if you just make an account. So if you don't want to run anything, check it out on Google. And then some of the other examples I had, MicroK8, Spancha, and OKD. Yeah, anyone have any questions? There's a lot of kube. Who's ready to deploy the one kube cluster? I was ready. Anthony's ready. Anthony's deploying so much kube right now. So yeah, thank you guys.